Now we're going to continue our study of graphing motion. Our objectives are going to be to construct and interpret graphs of position, velocity, and acceleration versus time, and then determine what the slopes and the areas under these curves mean. A great way to look at a diagram would be a particle diagram. A great way to look at motion would be a particle diagram. You can kind of think of it almost as a car driving with a leaky oil leak. And the dots are going to represent the motion of it. So the top one would be fast because the dots are farther apart. The bottom one would be slow because the dots are closer together. Take a minute to look at each one of those cases below and see if you can figure out what's going on in each case. You can pause the video here. It probably is a good idea for you to make a prediction first before you listen to the explanation. Okay, you should be back by now. This is going to represent constant speed. So constant speed. Because the speed's not changing any for each value of time. Okay, this one here is, you see the dots are getting farther and farther apart. That means your speed is increasing, therefore it's accelerating. Cool. And if I look at Z, now the dots are getting closer together, so what I have here is a negative acceleration. The object's slowing down. Now, when I first take a look at a graph, I've got a position versus time graph or displacement versus time graph. It's oftentimes a good idea to break it down into segments and then examine each individual segment. So, for example, the first segment would be this segment here. Just that first segment there. What's happening there? Well, obviously the displacement is increasing. It's linear. And the slope's the same, so therefore that's constant speed. So constant speed. C, speed. Now, if I look at the top interval, well, I'm staying at 5 meters the whole time. That's rest. I'm not moving at all there. And coming back, now I'm going back from 5 to 0 displacement, so therefore it's constant velocity, but in this case it's actually a negative velocity since it's the opposite of the direction that we called positive. Now, the slope of a position time graph. Well, slope is going to be rise over run. Go back to the old original way that you remember. There's two ways you can do it. You can put in your values and you have displacement over time. Sorry, I'm not real good writing on my finger. Displacement over time is velocity. The other way you can do it is you can say rise over run and do it with units. And it's going to be the change in meters divided by the change in seconds. And those are velocity units. So therefore you can take a look at what it is. For example, for the first segment, well, your rise is 5 meters divided by your run of 5 centimeters. So your first one is 1 meter per second. This one has no slope, therefore it's 0. Now coming back down here, I'm going from my rise is actually negative 5. So it's negative 5 divided by 2.5, so it's negative 2 meters per second. So the slope of a position time graph will give you the average velocity during that time. Break it up into segments that you can see. So what I've done now is I've actually graph the velocity versus time of this particular set of data. And it's the same numbers I had before. I have a rise of 5. Right here I have a rise of 5 divided by a run of 5. So I have 1 meter per second right there. This area is at rest. The slope is 0. And then this area down here is negative 2, so that's the way I would graph it. I'm going to leave these as straight lines now. You can't instantaneously accelerate and change velocities, but it's close enough that we can have it act as a straight line. Now here's kind of a neat thing. The two things I can do with graphs is I can calculate slopes, and I can also calculate areas under the curve. So let's take a look at the area under the curve of velocity time graph. And the reason I want to do that is area is always going to be some base times height. Well, let's say I want to look at this area right here. Well, the base is 5 seconds times the height of 1 meter per second is going to leave me with 5 meters. And if you think about it, that matches up with that point right there. It's gone 5 meters. Now on this one, there is no area under the curve, so therefore that doesn't help me any. With this one, since I'm falling, it's going to be a negative value. And if I put in that, it's going to be 2 times 2.5, which is negative 5 meters, which accounts for this side of it here. So the area under a velocity time graph actually gives you the displacement. If you take a look at that, that's a very powerful thing, because a velocity time graph, the area under the curve, can actually give you the displacement. Velocity time graphs are the best graphs ever. The reason the velocity time graphs are the best graphs ever, because the slope of a velocity time graph gives you acceleration, because slope is going to be rise over run. So it's going to be the change in speed divided by time, and change in speed divided by time is acceleration. So if I want to calculate the slope for the first 5 seconds, I'm going to say A is equal to, well, it rose to 10 meters per second divided by 4 seconds is equal to 2.5 meters per second, or meters per second squared. I can live with either one. Now, if I want to go total displacement for the entire 6-second interval, remember, displacement is area under the curve. I'm going to have to break it into things that I can handle. So I'm going to break it into 2 separate areas. For the first one, I'm going to go 1/2 base times height, so 1/2 10 meters per second times 4 seconds. 1/2 of 40 is 20 meters. Now for the second interval here, I simply take base times height, 10 meters BH. 10 meters per second times 2 seconds, 20 meters. Total distance, 40 meters. Just add them up. Now the slope of a velocity time graph gives you acceleration. If I take the area under the curve of an acceleration time graph, I'm going to get the change in velocity. That should be delta V. So if I have something like this, delta V, well, I get, hold on just a second. Okay, I'm back. Let's take a look at this real quick. If I look at the area under the curve, so if I say this area right here, if I say this area right here, well, if I'm changing 10 meters per second, 10 times 1, my change in speed is 10 meters per second. If I look at this area, now I'm talking about this whole thing. What I'm talking now is my change in velocity is 10 times 2, or 20 meters per second. Now, you're not asked to do that a lot. Velocity time graphs are the best ones in the world. Okay, let's real quickly look at how we go from one graph to the other. And I want to go x versus t, v versus t, and a versus t. And watch what happens when I go this way. If I go slope, The slope of a position time graph is velocity. The slope of a velocity time graph gives us acceleration. Now, if I'm going the other way, the area under an acceleration time graph gives me velocity. The area under a velocity time graph gives me position. So therefore, you can go back and forth between them by thinking slopes and areas. Anytime you see graphs, you want to think slopes and areas. Okay, as a quick review, if you have a position time graph, this is a velocity time graph, and this is an acceleration time graph. If an object's moving with constant velocity, remember, one of the key things to do with this is think about something that's constant velocity. Cruise control is a good example. Or if you're out for a slow jog, something like that, where you're not, see if you can create those three diagrams. Pause it, see if you can create it. Okay, it should be back now. Constant velocity means your speed is changing, but it's changing by a constant amount. Constant velocity means your speed's not changing, and all of your speed is not changing, you don't have any acceleration. So that's what the three graphs should look like. Now, for an object moving at constant acceleration, we can do the same thing. I think sometimes it helps to not start with a position time graph. But once you get the hang of it, and you'll see that in the lab, that once you get the hang of it, I don't think it's a problem. Key thing there is constant acceleration means your speed is changing by a constant amount. That means your acceleration is a constant value. This is a parabola. It becomes a parabola because of the x is proportional to something times t squared, and that's what forces it to be a parabola. So which graph best shows a car on cruise control? What's going to happen if you're on cruise control? Which one of those works? Think about what cruise control does and see if you can practically guess. Write down your best answer for part of your homework. Now let's take a look at which graph would best show a block sliding down a frictionless inclined plane. So in other words, you're going down a snow hill on your snowboard, and it's frictionless. What would happen to you? Write that down in your homework. I hope this helped. We'll spend a little more time on this in class.